Hi everyone, it's Matthew here. Today I'm going to be teaching you the F test, and I want you guys to think of this as sort of the prelude to discussing about regression. The idea is you want to know what it is when you actually see things in the output, the regression output. And so knowing the F test is going to give you a little bit of a leg up into knowing what you're actually seeing on the regression output, what's actually happening. So let's get started. I'm going to share my screen. So formally, we've had discussions on statistics, and I've been advising you guys to draw 3 lines and a normal curve. So like when you've done hypothesis testing, maybe one line is t, one line is x bar, where your sample means. You're drawing a normal curve, one line is p. And then you've been doing hypothesis testing, where, you're assuming some null mean, some assumed state of affairs, and you're comparing it against the sample mean. Let's just say the sample mean's over here. If these two means are close together, then you would say something like, I do not reject the null hypothesis. If these means are far apart, you would say something like, I do reject the null hypothesis. And specifically what I'm thinking about here is a null hypothesis where your mean is equal to x bar, and the alternative hypothesis where your mean is not equal to x bar. So what is the F-test? Well, the point being, the F-test is you can do this same thing, but with variances. So how you calculate F is equal to some variance of one sample over some variance of another sample. Or you can say F is equal to some variance type in your current data set versus another type of variance in your current data set. It doesn't have to be two samples. It could be two types of different variances in one sample. And I want you to see a kind of logic here. If one of your variances is 2.5 and another one of your variances are 1.5, as they get closer together, 1.5 goes up to get closer to 2.5, 2.5 goes down to get closer to 1.5. This is going to merge to be 2 over 2 or 1. So with F-tests, this brings a rule that the closer your F is to 1, the more likely your variances are the same. So the closer your F is to 1, the more likely you are going to say that the variance 1 is equal to the variance 2. Now let me give you another example. What if your F is 9? It's not very close to 1. And you can sort of say 9, if you simplify that fraction, 9 is really 9 over 1. So whatever your variances are when they're simplified, if you have a variance of an f of 9, then you're really having an f of 9 over 1. What this means then is that this variance 1 is 9 times greater than this variance 2. So it makes sense. You would reject the null in this case, that the variances are the same, in favor of the alternative hypothesis, that variance 1 is not equal to variance 2. Now let me just put some labeling on this tab. This is hypothesis testing means. This is the F-test. Now, what I want you guys to think about is that this plays into regression. So regression in its simplest form, it's just dependent variable, independent variable. And let's just say you have a relationship between your IV and your DV. That's what all these dots are for. And so you can draw a line of best fit through them. I'll do that right now. You can also draw the mean of the dependent variable. This is the mean of the dependent variable. In this chart here, what I want you guys to see is that there are two forms of variances here. And so we're going to focus on this data point right here. I'm going to do it in a different color. So going to this data point, and actually I'm going to do it with a pen. Going to this data point, there's two forms of variances here. Variance 1 is from the mean to the line of best fit. And then variance 2 is from the line of best fit to your data. First thing I want you guys to see is that these two variances add up to total variance. So any data set that you encounter that has an independent variable and a dependent variable, if you draw a line of best fit through it, you'll get two forms of variance. You add them up, you're going to get total variance. Second thing I want you to see is that this form of variance here is called the mean squared of the regression. And this form of variance here is either called the mean squared of the residuals, or sometimes it's called mean squared error. And what you'll often see in regression is an F-test, where it compares these two variances, mean squared regression over mean squared error. And what's happening here is if your mean squared regression is bigger than your error, it makes sense that this F is going to be greater than 1. If your mean squared of regression is less than your mean squared of error, it makes sense that your F is going to be between 0 and 1, not including 0 and not including 1. If your mean squared regression is the same as your mean squared error, like we discussed here, when the two F's are the same, you get 1, and you get an F of 1. If you have no relationship at all, you get an F of 0 because all you have is mean squared error, and you have no mean squared regression. So let me just delineate these cases. This is mean squared regression is bigger than mean squared error. You can kind of see that if you have a bigger number on top of this F, you're going to have something greater than 1. Sorry, this is wrong. This is this case right here. Mean squared regression is bigger than error. Mean squared regression is smaller than mean squared error. This kind of makes sense. If you have a larger number on the bottom than the top, you're going to have some fraction between 0 and 1. Mean squared regression is the same as the mean squared error. This kind of makes sense. If these two numbers are the same, they are 1, it's like 2 over 2 or 3 over 3. It kind of makes sense. And mean squared error is the only thing that exists. The reason why knowing these cases is important is because if there is absolutely no relationship between your IV and your DV in regression, you have a data set that kind of looks like this when you do a scatter plot. And so the only line of best fit that exists in something like this for your dependent variable is just a line straight through the middle. It's your mean of the dependent variable. If you sort of look at these definitions, the mean squared residual is just the distance from the data point to the line of best fit. So the line of best fit is this mean in the case of no relationship. So the distance is this purple line. If you look at this definition, the mean squared regression variance is from the line of best fit to the mean. There's no mean of squared regression statistic. So what ends up happening in a case of no relationship, your f gets closer and closer to 0. And so what's happening in regression then is that it's testing, is there a slope to your line of best fit? In this case, this is your line of best fit, LBF. There's no slope to it, it's flat. So if there's no slope, it means there's no relationship between your IV and your DV. So you have an f of 0. If there is a slope, like this chart, it means that there is a relationship. You don't have an f of 0. And it can either be a small relationship. So in case of small, tiny relationships, you would expect the error to be greater than the regression. It could be a y is equal to x kind of relationship. So in case of even relationships where the variances are equal, you would expect an f close to 1. And in the case where your data is actually predicting something, it's actually useful. You can actually use it for prediction. Your line of best fit is going to predict more variance, is going to have more variances underneath it than your error. So again, this is just a high level overview of the F-test with the express purpose of trying to give you an understanding of sort of what's going on when you see it in the regression output. I will definitely talk about regression further. I hope this was helpful. Thanks.